Hi, welcome to this video on linear programming duality. In this video, we're going to prove complementary slackness. So just to remind you what the CS conditions are before we go ahead and prove them, what we have is a primal dual pair of linear programs, max and min, and x bar and y bar are a primal dual pair of feasible solutions. So x bar is feasible for max and y bar is feasible for min. And so what we can say then is that x bar and y bar are a primal dual optimal pair for max and min if and only if these following two conditions hold. So the first condition is that for every variable xj of the maximization problem, either that the component for our feasible solution is 0, or the corresponding constraint in the minimization problem is tight with respect to y bar. So what we're saying is when you plug in y bar to that particular constraint in consideration of the minimization problem, does that constraint hold tight with equality? And then so vice versa, you just reverse the rules of everything now for the second type of condition. So for every variable yi of the minimization problem, either the variable component is 0 for our feasible solution y bar, or the corresponding constraint in the maximization problem is tight now with respect to x bar, because we're plugging x bar into the constraint for the maximization problem. So if all of those conditions hold, then that's exactly when your primal dual feasible solutions are actually a primal dual pair of optimal solutions. So let's see how that's actually going to be proven. But first, let's just note that we're going to do this in a special case of linear programming formulations. So this right here on the bottom that you can see is the formulation we'll do it for. So we have a primal dual pair of max and min linear programs here, where the maximization problem is matrix inequality constraints, where all the inequality constraints are less than or equal to constraints, and the variables are all greater than or equal to 0. And then correspondingly, you can see here for the dual. So all the constraints are of a uniform type. And now this is just one type of formulation for a linear program. If we wanted to do this in total generality, we would be looking at this, which is just many more constraints, many more types of constraints, that is. And so I will just emphasize that the logic that we're going to use for this special case entirely generalizes to this general case here. It's just a natural extension of what we're doing. There's no new ideas involved in proving the general case. It's just more heavy-duty notation now, because there's more things you have to deal with constraint-wise and correspondingly notation-wise. So it just becomes more of a mess, and the notation kind of obscures the one idea that's involved in the proof. So there's no need to obscure it. Let's just keep things clean and simple and prove it in the special case. And if you really want to prove it in the general case, you can, using the same exact idea. Now you just have to check for more cases of things that can happen, is all. But okay, so we'll prove it in this special clean case that we have up top here. So let's see how we can derive the complementary slackness conditions in this special case now. Okay, so proof. Well, first of all, what we know, just to remind you, so we'll have x bar and y bar. They will be feasible solutions for these two linear programs. I'll call the linear program on the left, I'll call that P, and the one on the right, we'll call it D for primal and dual. It's just a convention, so that whenever I say primal, I'm referring to the maximization problem, and whenever I say dual, I'm referring to the minimization problem. We could have reversed those roles, it doesn't matter, but we're just picking a convention and sticking with it. And then also, it's going to be actually tedious to keep writing the x bar and y bar, the bars over the x and y over and over. So let's just say x bar equals x and y bar equals y. And so that's a bit of an abuse of notation, just to keep things simple so we don't have to clutter things with all these bars. But anyways, when we're referring to x and y, we're referring to the specific feasible solutions that we have in our proof here. Okay, so what do we know starting off for a primal dual pair of linear programs? For these two feasible solutions, what we know is that when we plug them in, we'll get that B transpose Y is greater than or equal to C transpose X. So that's automatically true always in every case by weak duality. So weak duality always tells us that we have that. So in other words, B transpose Y minus C transpose X, that difference is non-negative. And in fact, so what we can say then is that difference, B transpose Y minus C transpose X, will be exactly equal to 0 if and only if X and Y are a primal dual optimal pair. So let me write that down. Okay, and so the reason that that's true is by strong duality. We know by strong duality that the output values for the optimal values for a primal dual pair of linear programs which both have feasible solutions, those optimal values are both going to be equal to each other. So the difference is going to be exactly 0. So when you take your two solutions, your two feasible solutions, when you plug them into their respective objective functions and you take their difference, if you get something that's exactly equal to 0, you know that they must have both been optimal. And if you don't, then you know that at least one of them must not have been optimal. So that's already a way that we can see that x and y are whether or not they're optimal or not. So we're just going to rewrite this left-hand side that you see over here, and we'll rewrite it in a way that we'll see that the complementary slackness conditions are effectively capture what we want. So let me stop being so vague and just write down some technical things here. Okay, so this difference B transpose Y minus C transpose X, we're going to rewrite this. So the left-hand side, that's what B transpose Y minus C transpose X is. First of all, that's Y transpose B minus X transpose C is a more convenient way for us to write this because I want to write this as a mixture of the constraints. So in the complementary slackness constraints conditions, you'll see that either a dual variable is 0 or a primal constraint is tight. And so what I want then is to be able to write my dual variables with my primal constraints. So Y transpose B, you see that the B data appears, not only does it appear in the dual objective coefficients, it also appears as the right-hand side components of the primal constraints. So let's replace the B here with AX. You'll see how we do that. It'll be Y, so Y transpose AX is the same thing as Y transpose B, except that AX is less than or equal to B. It's not exactly equal to B. So we need to add on a bit more. We need to add on the slack that's left over from AX going all the way up to B, because for each of the components of the vector A times X, those components are each individually going to be less than or equal to the components of B. And so, anyways, what we need is the slack. So B minus AX is the slack. Okay, so now we've written Y transpose B. You can see that the Y transpose AX's will cancel with each other. And what we'll be left with is Y transpose B. So this is the same thing as Y transpose B. But the advantage of writing things this way is that we have a sort of a combination of the dual variables and the primal constraints. You can see that the constraint AX portion of the constraints of the primal appears alongside the dual variables Y transpose in the same term. So this will at least give you some idea that we're getting closer to the complementary slackness conditions because we're writing things in that way. So we need to do the same thing now for the X transpose C part. So we've done the Y transpose B, so now X transpose C goes the same way. So we'll have X transpose A transpose Y, because the A transpose Y is the left-hand side of the constraints of the dual constraints. But now we have a surplus because X transpose times A transpose Y, that's going to be larger. A transpose Y is larger than C. So we have a surplus there, so we need to subtract that surplus off. So minus X transpose times what the surplus is, which is A transpose Y minus C. Okay? And so this part right here is the same thing as X transpose C. You can see that the X transpose A transpose Y's will cancel with each other, and then we'll have a minus minus X transpose C. So that's a positive X transpose C is what's inside the parentheses here, or the brackets here, and that's what we're subtracting off. So this really is the same thing. We've just rewritten it. Okay, and now we can do a bit of a simplification because Y transpose AX and X transpose A transpose Y are actually the same thing. You see, they're both numbers. They're not matrices, they're not vectors, they're just numbers. And so they're transposes of each other as well. And so the transpose of a number, or a 1-by-1 matrix, in other words, is itself. So this is the same value. Y transpose AX is equal to X transpose A transpose Y. And therefore, because we have one with a plus sign in front and one with a minus sign over here, they cancel. And so these terms will go away. And so what we're left with then is Y transpose B minus AX. Let me make that a more legible A. And plus now x transpose A transpose Y minus C. Okay, so the minus minus became a plus. All right, now what is the advantage of having done this, besides that we're supposed to be getting closer to complementary slackness? Well, maybe it'll become clear in just one more step, but let me just point out that each of these components are all non-negative right now. The y's are non-negative, the b minus ax is non-negative, x is non-negative, and the A transpose Y minus C is non-negative. And that all comes from the fact that that's encoded in the constraints of the primal dual pair of linear programs here. So then overall, because we're taking a product of non-negative things and a sum of non-negative things, then the overall term is going to be greater than or equal to 0. However, that's not new information, because this is what originally was written as B transpose Y minus C transpose X, and we already knew that that was non-negative by weak duality. So that's not telling us anything new, but we'll be able to manipulate this term in its new form now, as you'll see in just a moment. So what we can do is we can write this as as the sum. We're summing over all the indices I of yi times bi minus rho I of a transpose x. Okay, so that takes care of the y transpose times b minus ax part. Do you see what happened? We're just, you know that for every single component of the dual variables y, there is a constraint of the primal constraints, and the primal constraints are of the form ax less than or equal to b. So for a particular constraint, there's a row of the matrix A times the vector x, and that's less than or equal to the right-hand side component of the vector b, and so we're taking the difference here. So this is bi minus the left-hand side there. So anyway, so each of these individual terms are also non-negative. So that takes care of the y's and the primal constraints. So now let's take care of the x's and the dual constraints. So now plus, we're summing over indices j, xj times aj transpose y minus cj. Okay, so this is the same thing. These constraints over here, this is an individual constraint of the dual matrix constraints, and then this is a primal variable, and they come in these, get paired like this because there's a correspondence between primal variables and dual matrix constraints. So anyways, this is just rewriting what the dot product of these vectors are, and it's this right here. So I should put an equals there. And now the point is that it's not only that the overall terms are going to be non-negative, it's actually that each of the individual components are all going to be non-negative. Because the vectors are all non-negative, that means all the components of the vectors are non-negative. So yi is non-negative. bi minus rho I of a transpose x is also non-negative. So same thing for everything here. So all the individual terms are non-negative, and okay, so that tells us something now. Since each of the individual terms is non-negative, there's no way you can get any cancellation between terms, because there would need to be something negative to cancel with something positive, but there are no negative things. As we're saying here, this is a product and sums of non-negative things is still going to be something non-negative. And also we know that this slightly more convoluted thing that we've written down here is actually just B transpose Y minus C transpose X in disguise. They're the same thing, and we already know that we already wrote above B transpose Y minus C transpose X is going to be 0 if and only if the X and Y are a primal dual optimal pair. So in other words, this thing down here is going to be 0 if and only if X and Y are a primal dual optimal pair. So how is it possible for this thing down here to be equal to 0? Because it's a product and sum of non-negative things, again, so what that means is that each of the individual terms all had to be equal to 0. So what we'll say then is that this equals 0 if and only if yi times bi minus rho I of a transpose x equals 0 for all I, and xj times aj transpose y minus cj equals 0 for all indices j. So those things all need to be true. And this is effectively now the complementary slackness conditions. Oh, I forgot a parentheses, by the way. So how do we see this as the complementary slackness conditions? Well, what does it mean for a product of two numbers to be equal to 0? Well, that means that either yi equals 0 or bi minus rho I of a transpose x equals 0. So one of those two things needs to be equal to 0. Same thing down below. Either xj equals 0 or aj transpose y minus cj equals 0. And now it's even more clear that these are the complementary slackness conditions because either we have a variable that's a component that's equal to 0 or the corresponding constraint is tight. Why is this the same thing as the corresponding constraint is tight? Because this is an equality here. So let's just rewrite things one more time. So this is if and only if. Okay, so I've rewritten the constraints here. All I've done is I've just rewritten them, except that the b's and the c's got moved to the other side of the equation. So now we have equalities here. And then now what we know is that these are the constraints that appear in the primal and dual. The rho IA transpose X is a constraint in the primal, except that in the primal, for instance, there would have been a less than or equal to rather than an equality. And same thing here, there would have been a greater than or equal to rather than an equality. But what we're saying is that, in fact, it must hold with equality. Or in other words, the constraint is tight. So either that's happening or the corresponding variable associated to that constraint is 0. So one of those two things, and this is exactly the complementary slackness conditions. So let me just circle that, and that is the CS conditions. Okay, and so this then is the proof, because we've just said that the only way for us to have a primal dual optimal pair is for B transpose Y minus C transpose X to equal 0, and the only way for that to happen is for this to happen, and this is the complementary slackness conditions. So just chaining those things together, having a primal dual optimal pair of solutions is equivalent to having the complementary slackness conditions hold. And so that's the proof. So in summary, what we did was we just started with this difference here coming from weak duality, and we said by strong duality, actually, the only way for this to be a primal dual optimal pair of solutions is for this difference to be exactly 0. And then we just did some algebra, and we rewrote and rewrote and rewrote until we got to this stage down here. And this is just an algebraic manipulation of the original difference of the objective functions equaling 0. The only way for that to equal 0 is for these things down here to be true. And so that's how the proof of complementary slackness goes. So that covers it for the content of this video. In the next video, look for some ways we can utilize the complementary slackness conditions, but that will be for the next video. So stay tuned for that, and thank you for watching.